Okay, so this screencast is on oxidation reduction reactions. This is our third type of reaction that we're covering in our course. The first reaction we talked about, a category, was precipitation reactions. And in precipitation reactions, we have cations and anions combining to form insoluble ionic compounds. So that was the first category we talked about. The second category of reactions we talked about were neutralizations, where essentially we had hydrogen ions and hydroxide ions combining to form water. The third category we're going to talk about are a category of reactions called oxidation reduction. And they're a pair. There's two kinds of reactions here. There's oxidation and reduction, but they always come in pairs. And this category of reactions, sometimes called redox, involves electron transfer between reactants. All right, so oxidation reduction. The first half of that is oxidation. Oxidation is defined as the loss of electrons by an atom or an ion or a substance. And a loss of electrons will make something more positive. For example, when you put solid calcium metal into an acid, which right now we'll just talk about the hydrogen ion there, into an acid, it will cause the following to happen. You'll get calcium 2+ ion and hydrogen gas. If hydrogen is the product of something, it will usually be H2 in its gas form. The calcium, when it's a solid, has a 0 net charge. And when it's an ion, it has a 2+ net charge. Notice that when we're talking about the charge of an ion, we do the number then the sign, so it is a 2+ net charge. You'll see soon why we do that. It has a 2+ net charge. So to go from 0 net charge to 2+ net charge, we lose 2 electrons. So losing electrons is oxidation. Why is it called oxidation? Historically, the first reactions they studied with this phenomenon of electron transfer were reactions with oxygen. So an example of an oxidation, again, might be calcium solid plus oxygen gas yields calcium oxide solid. Now the calcium here went again from a 0 net charge as a solid to a 2+ charge. So that is oxidation. However, if we look at the oxygen, it went from a 0 charge to a 2- charge. That's a gain of electrons. A gain of electrons is called reduction. Okay, so the gain of electrons by a substance in a reaction is called reduction. They will always come in a pair. So if something loses electrons, something else will gain. So that's why we call them oxidation reduction reactions. They're always together. Okay, so if we want to look at oxidation reduction reactions, we're going to have to focus on the charges of the species or the chemicals in those reactions. And we do that through a system called oxidation numbers. And there's some rules to this. So you need to know how to assign oxidation numbers. Some of the rules are easy, like the first rule. Atoms in their elemental form always have an oxidation number of 0. Or an oxidation state, we call it. For example, the hydrogen in hydrogen gas has an oxidation state of 0. We write like this. We generally draw the oxidation states above the species. Phosphorus in P4 solid has an oxidation state of 0. So that's rule number 1. Rule number 2 is that monatomic ions, their oxidation number or oxidation state is their charge. So an example of that would be in potassium sulfide. The potassium in that has a 1+ charge, potassium ion. So its oxidation state is going to be +1. The sulfur has a 2- charge, so its oxidation state is going to be -2. Notice I'm coming back to why we write charges as the number then the sign, like this, but the oxidation state is written as the sign and the number, so we can distinguish between them. Oxidation state is +1, but the charge is 1+. Okay? So things that are easy to remember in that case, the group 1s, like lithium, sodium, potassium, those all have a +1 or a 1+ charge. They will have an oxidation state of +1. Category or group 2A, so your beryllium, magnesium, calcium, those are going to have 2+ charges, so their oxidation state will be +2. Aluminum, which is in group 3, will have a 3+ charge, so its oxidation state is going to be +3. All right, rule number 3. Nonmetals almost always, notice I say almost always, have a negative oxidation state or number. Okay? For example, oxygen is usually an oxidation state of -2. However, if it's in a peroxide, like O2 2-, each O has a -1 number, oxidation number. The other one that you need to be aware of is hydrogen. H will have a +1 oxidation state when paired with nonmetals. And it will have a -1 oxidation state with metals. So those you need to be aware of. Final rule is that the sum of the oxidation numbers in a neutral compound has to be 0. So this is useful when you don't know a neutral one of the oxidation states, but you know maybe some of the other ones in it. You can use math to figure out what the remaining compound or the remaining atom's oxidation number should be based on knowing the other ones in the compound. So it has to be 0 in a neutral compound. And what follows from that is that in polyatomic ions, the sum of the oxidation numbers has to be the charge of the ion. And I'll show you an example of that right now. All right, so for example, your polyatomic ion sulfate. It's an SO4 2-. Okay, so in this case, because it's not a peroxide, we're going to start by assigning the oxidation state to the oxygen. We know that oxygen is almost always a -2. Okay, so we need to figure out what sulfur's is. There's no rule that specifically governs sulfur. However, we know that the total of sulfur, which I'll call X, plus 4 times -2, because there are 4 oxygens, each with an oxidation state of -2, has to equal -2, because the charge is 2-. So when we solve that, we find that X has to be +6. So it turns out that the oxidation state for sulfur in this compound is a +6. So that this compound comes out to have a charge, or this polyatomic ion comes out to have a charge of 2-. All right, let's do a few more examples of this. First one is the first one is what is the oxidation state of the sulfur in hydrogen sulfide. The second one is the sulfur in the S8 compound. So looking at the sulfur in all of these compounds, what is the oxidation state of the sulfur? Maybe take a pause, see if you can assign it, and and when you unpause, I'll give you the answer. All right, in hydrogen sulfide, hydrogen is going to be a +1, so sulfur has to be a -2 so that they balance out to 0. S8 is elemental, so its oxidation state, the sulfur's oxidation state is 0 in that case. Actually, the better way to write that is like this. In sulfur chloride, SCl2, the chloride is a -1. Oops. -1. So that means that the sulfur has to be a +2, so they come out to be neutral. And in sodium sulfite, we know that sodium is always going to be a +1. There are 2 of those, so 2 times 1 plus an oxygen here is going to be a -2 plus x plus -6 is going to equal 0. So x in this case has to be equal to +4. So the sulfur's oxidation state in that is +4. And that all adds up to 0. So that's an example that you can work your way through. All right, let's look and give you another set of example questions for tomorrow. Practice these tonight, come in tomorrow with some of these. I'm going to write, I'm going to highlight the letter. So phosphorus in P2O5, sodium in NaH, Cr2O7, chromium in that. Let me highlight these as I go along. So phosphorus, oops, no, hydrogen. Chromium. Then the tin in tin 4 bromide. And finally, the oxygen in barium oxide. See if you can come up with the oxidation numbers. So assign oxidation numbers to the highlighted elements. That's the example you should try for class tomorrow. All right, so moving on from assigning oxidation states, we want to look at the kinds of redox reactions and how assigning oxidation states will help us. We're going to be using redox reactions quite a bit, especially in our electrochemistry unit. So you need to be familiar with them, and they will come up a lot. We're actually acid-base titrations. We'll look at redox titrations, all sorts of things having to do with redox. So the one you might be most familiar with that's a redox reaction is the oxidation of metals by acids and salts. These are what you might have heard as your single displacement reactions. If you were in chemistry here in a previous year, you remember making copper. The making copper lab is a single displacement. The general form of these kind of reactions is that you have A plus BX gives AX plus B. So A and the B switch places. For example, here are 2 reactions that are considered to be redox reactions or single displacement. Solid zinc reacts with hydrobromic acid to yield zinc bromide, or zinc 2 bromide. Zinc 4 bromide? Zinc 2. Zinc 2 bromide. Plus hydrogen gas. Like I said, if it's going to be hydrogen, it's going to be H2 gas. Or you might look at manganese. Solid manganese reacts with lead 2 nitrate to yield manganese 2 nitrate plus solid lead. So with these, what you're going to need to be able to do is assign the oxidation states and figure out which reaction is reduction and which one is oxidation. So let's look at an example of that. Magnesium. Solid magnesium reacts with hydrochloric acid to yield magnesium chloride and hydrogen gas. All right, first thing we're going to do is we're going to assign the oxidation states. Starting with magnesium, we know that it has an oxidation state of 0 because it's an element. Hydrogen has an oxidation state of 0 because it is an element, right? Elemental form. Moving over to the HCl, we know that chloride is going to be -1 and hydrogen is going to be +1 because when hydrogen is bonded to a nonmetal, it is a +1. And chloride ion or chlorine is a nonmetal. Magnesium, this is a monatomic ion. It's magnesium 2+ ion, so we're going to give it a +2. Chlorine is a -1. And now we can look at who has lost and gained electrons. So let's look first at magnesium. Magnesium has gone from a 0 net charge or a 0 oxidation state to a +2 oxidation state. To go from 0 to +2, we have to lose electrons. Losing electrons equals oxidation. Magnesium was oxidized in this case. Then we can look at hydrogen. Hydrogen goes from a +1 oxidation state to a 0 oxidation state. I should do it this way. And to go from +1 to 0, you have to gain electrons, which is reduction. Okay, chlorine, you'll notice, goes from 1- to 1-. It's your spectator ion. Nothing happened there. So, a nice mnemonic for you to help you remember which one is oxidation, which one is reduction, is Leo the lion says grr. Leo the lion says grr. You have lose electrons is oxidation, gain electrons is reduction. So what you've got there is a nice little mnemonic for remembering that. The next step in this would be to take this equation that we already wrote and write it as a net ionic equation. So the net ionic equation for this oxidation reduction reaction is that Mg solid plus 2H plus aqueous yielded MgCl2 plus H2 gas. Because those are the things that changed, because this is actually, oh wait, it should just be Mg2 plus aqueous yields Mg2 plus H2 gas. So that is the net ionic equation for that one. All right, here's another example. So you can work through this again. Let's say that we have solid iron plus nickel nitrate, nickel 2 nitrate, aqueous, and that yields iron 2 nitrate plus solid nickel. So writing the net ionic equation, we want to find out who has been oxidized and who has been reduced. So let's look at that. Iron starts out as a solid, that's 0. Nickel over here is a solid. Nickel in this one is going to have, well, iron over here, let's go to, nickel in this one is going to have a +2 charge, and iron is going to have a +2 charge. So we can look at this from 0 to +2, that is a loss of electrons. So it was oxidized. And from +2 to 0 is a gain, so it was reduced. And the net ionic equation for this then, so the net ionic equation for this reaction is solid iron plus nickel 2 plus ion yields iron 2 plus ion, oops, I wrote it out there, plus nickel, solid nickel. And so we can look at this then and try to figure out, what was oxidized from this. It's pretty easy to see. From 0 to +2 must be a loss of electrons. So that's easy. For class, the example I'd like you to try is to write the molecular and net ionic equation for the following reaction. The reaction between solid magnesium and cobalt to sulfate. So write both the molecular and net ionic equations for those and answer the questions: what is oxidized, which species is oxidized, and what is reduced. So give yourself a little practice on that.